All right, let's start over. Okay, as we just said, guys, some non-metals are less likely to gain electrons than others. Okay, so group 14, if we're looking at the periodic table, group 14, anything in group 14 will have how many valence electrons? 4, right? Group 14 has 4 valence electrons. So, in order for group 14 to be stable, they either need to gain 4 or lose 4, okay? So, anything in group 14 has either got to gain 4 or lose 4. Do y'all see the problem right off the bat? What's the obvious problem? Either gain 4 or lose 4. I mean, when we look at sodium, remember sodium is either gain 7 or lose 1. Pretty obvious solution, right? Lose 1. If we're looking at fluorine, fluorine is either gain 1 or lose 7. Pretty obvious solution, right? If we look at carbon, either gain 4 or lose 4. It's not as obvious not as obvious of a solution there, right? Okay. So for elements in that group, okay, loss or gain is going to take a lot of energy. Okay, to gain 4 electrons or to lose 4 electrons, either way is going to take a lot of energy. Okay, and reactions don't generally like to do things that take a lot of energy. So in general, the least energy option is what happens. Okay, so for the things in group 14, and not in just group 14, a lot of the nonmetals, in fact, okay, instead of taking electrons or losing electrons, what they're going to do is just share electrons with other atoms. Okay, so they're not going to give 4, they're not going to receive 4, they're just going to share 4. Okay, so they'll share their 4, another one will share its 4, and now they both have 8. Okay? Right. Okay. We're going to take a desk outside. Would a gentleman like to grab her desk, please? I got it. Okay. Everybody still on the same page? Okay.
When you were talking about were you saying non-metals could lose or gain, or was it just like that?
I mean, any atom could lose or gain electrons, but nonmetals tend to gain. And the reason why is it's easier to gain 1 or 2 than it is to lose 6. Okay. So they're going to tend to share electrons. Okay, and what we're going to call that when they share an electron is a covalent bond. Okay, if you make a covenant with somebody, that's like it's like a promise, or like a promising statement. Okay, so a covalent bond is almost like they're agreeing to share some electrons. Okay, I'm personifying atoms here, but you get the picture. Okay, so here's my little way of remembering ionic or covalent bonds. Okay, we're going to let all the metals, okay, so everything that's a metal, we'll let metals represent Santa Claus, okay, or be represented by Santa Claus. Give me some characteristics of Santa Claus.
Fat, jolly.
He's fat.
Worried.
He's very...
Oh, no.
Happy. Giving.
He's very giving, okay? So those are the 2 characteristics of Santa Claus we need to know. He's fat and he's very giving. And the same thing is true with metals, okay? Metals, they tend to be the bigger atoms. Okay, when I say bigger atoms, that means they have larger atomic radii. Okay, their valence electrons are very far out. Okay, in a non-metal, the valence electrons are closer in. Okay. And also metals tend to be very giving, right? They give away their electrons very freely. Okay, we're going to let the non-metals be represented by children, okay? So children, kind of greedy, not really the best at giving away things, or at least not all children. Children tend to be a little smaller, at least, very young children. And so we'll let children be the non-metals and Santa Claus be the metals, okay? So if I put a metal with a non-metal, that'd be Santa Claus with a child, then Santa Claus is going to give the child a toy, right? Makes sense, right? Okay, that would be giving away an electron. Okay, however, if I put a child with another child, are they just going to give up their toy?
No.
No, okay? I mean, what's the very best you can get them to do? Share. I mean, the very, very best you can get them to do is share, right? Okay, so you put two children together, you can get them to share. But what does a child prefer? To get a new toy from Santa Claus or to share with another kid? To get a new toy from Santa Claus. So what do the atoms tend to prefer to do? To make ionic bonds or to make covalent bonds? Ionic. Okay, so the ionic bonds are the bonds of preference, and the covalent bonds are just kind of like, hey, well, we got to. Okay. What is going to be the stronger bond, ionic or covalent? You can use the same example. Ionic. Okay, ionic is going to be the stronger bond. And if we dive into the chemistry, the reason why ionic is stronger is what holds ionic bonds together? The EF. Electric force. Is there an electric force holding covalent bonds together? No, because they don't become ions. Okay, so there's no electric force there. Make sense?
Hey, did you do that on purpose?
Do what on purpose? No, no, I didn't. No, that's good. All right. When I have a covalent bond, guys, that makes a molecule. Okay, so we call atoms bonded together covalently a molecule. We call atoms bonded together ionically a compound. Okay, what's easier? Well, what's another word for prison?
Jail.
A compound, right? Okay, is it easy to get out of jail? No. So is it easy to get out of an ionic bond? No, not so easy. Okay, so a compound would be an ionic bond. A molecule will be a covalent bond. Okay, the way I remember that, because sometimes I forget and remember which one's which, is if I have two things bonded together, we call that a diatomic molecule. And diatomic molecules are always covalent. So I just think diatomic molecule, okay, that's covalent. That's my way of remembering it. Maybe that's not a very good way, but that's my thing. Or you can think a compound is hard to get out of in the same way that an ionic bond is hard to get out of. Okay, good. All right, first, atoms can have multiple covalent bonds, but we're going to start with the case of only one. Okay, so a single covalent bond, guys, is made up of two shared electrons. And specifically, when I say two shared electrons, what I mean is that one atom is going to share one electron, and the other atom is going to share one electron. Okay, so that's how I end up with two electrons. Okay, a water molecule, guys, water is covalent, H2O. Okay, it has two single bonds. And a single bond, and the covalent bond does result in stability. And I want to take a second and look at that and see, and take a look at how that happens. Okay, so let's say I have water. That's going to be hydrogen, oxygen, and hydrogen, right? Right? Let's draw out the valence. How many valence electrons does hydrogen have? One. Because it's in group 1. How many? So hydrogen here once again has 1. How many valence electrons does oxygen have? 6. Because it's in group 16. Okay, so I have 1, 2, 3, 4, 5. What have I done? 6. There we go. Okay, so what results, guys, is hydrogen's going to move in closer. Okay, when it moves in closer, it makes a covalent bond right here. Okay, so these two electrons get shared between this oxygen and that hydrogen. I mean, the dark green belongs to the hydrogen, and the light green belongs to the oxygen. I should have done other than green, but you get the picture. Okay, and then right here, these move closer together. Makes a covalent bond. Let's count the valence electrons now that things are shared. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And how many does it want? 8. Hydrogen has 1, 2. This hydrogen has 1, 2. How many does hydrogen want? 2, and so it's stable. Good? Any questions? Okay, that's called a single covalent bond because there's only one bond between the oxygen and the hydrogen. Okay? Now there can be multiple covalent bonds between things. Okay, and so nitrogen is an example of that. When nitrogen when nitrogen bonds with itself, and if it's N2, we call that a diatomic molecule, okay, because it's two. Di means two, okay, so diatomic molecule. And so when nitrogen bonds with itself, it's going to form 3 bonds. And so let's look at that. Around this nitrogen here, let's count. I see 1, 2. I'm just going to draw on here. If I can get this to pull up. All right, so around nitrogen, I see 1, 2, 3, 4, 5 valence electrons. Is that right? 5? Yeah? And around this one, I see 1, 2, 3, 4, 5. Okay? When they move closer, okay, what I see is that these electrons here are going to get shared in the middle. Okay, so I see 1 covalent bond, 2 covalent bonds, 3 covalent bonds. Good so far? That would be called a triple covalent bond. Okay, once it makes that bond, let's count the valence electrons now. I see 1, 2, 3, 4, 5, 6, 7, 8 for this nitrogen, and 1, 2, 3, 4, 5, 6, 7, 8 for this nitrogen. Okay, so they both have 8 valence electrons now. Make sense? Easy, right? Huh? Now notice they both have 8. So part of me kind of wants to say, oh, that makes 16 electrons. There's not 16 electrons. Okay, if I add them all up, that's only 10 electrons. Okay. However, they're sharing the electrons in the middle. So they both kind of have 8. But they also both kind of don't have 8. Make sense? Huh? You say chemistry's hard. Okay, so let's go back to our example of Santa Claus and kids. Okay, I have 2 kids. We tell them they're going to have to share. If I had a timer, would one kid always have would they always have the toy for an equal amount of time? No. Okay. In general, one kid is going to have it a little bit longer. The other kid's going to have it not as much time. Which kid is going to have it longer typically? The one that's stronger, maybe the older one, or which one's faster, or the one that's trickier. But in covalent bonds, the same thing can happen. Okay. Okay. So the electrons are not always going to be shared equally. Okay, so some of those nonmetal atoms are a little bit greedier than the other ones. Okay, they tend to kind of hoard the electrons a little bit. And the general rule, guys, is the trend, the upper right-hand corner of the periodic table are the greediest ones. Okay, so looking over here at our periodic table, fluorine is going to be our upper right hand. Okay, we don't count the noble gases because they don't bond anyway. So fluorine is the most greedy one. Okay, and as we move away from fluorine diagonally, that gets less greedy. Okay, so which one is more greedy, fluorine or nitrogen? Fluorine. Okay, so which one is going to tend to have the electrons more often, fluorine or nitrogen? Fluorine. Okay. Okay, and that's called electronegativity. Fluorine is said to be more electronegative than nitrogen. But y'all don't need to know that word. Well, no? Yeah, you'll learn it next year. Okay, so are y'all interested in why they're more electronegative? I didn't figure you would be. Okay, I'm just going to skip that. All right, so when they have unequal sharing, okay, a lot of the time that's going to result in something called a polar molecule. Okay, the most famous example of a polar molecule is going to be water. Okay, so that's what we have up there. You see, I see 2 hydrogen atoms and 1 oxygen atom. And if we count the valence electrons, they would be satisfied. Okay, I mean, hydrogen here has 2, hydrogen has 2, and oxygen has 8 valence. Okay, so all is good. Okay, however, looking at our periodic table, guys, which one is going to hoard the electrons more, oxygen or hydrogen? Oxygen. Okay, oxygen tends to hoard the electrons more. So if the electrons are more frequently with oxygen, then that's going to make the oxygen tend to have a little bit of a charge in what polarity? Positive or negative? If it tends to hoard the electrons a little bit more, then that side is going to tend to be negative because it has more electrons. It didn't gain the electrons, but the electrons are more on that side. Okay, and since the hydrogen is not getting them quite as often, it's going to make that hydrogen side a little bit positive. Okay, so with polar molecules, guys, whichever one is closer to fluorine tends to have the negative side, and whichever one is farther away from fluorine tends to have the positive side. Thank you. That makes sense? This means yes, this means no. Okay. Y'all are it must be the rain outside. Okay. Anyway, the polarity of the water molecule gives us a lot of the features of the water molecule, and one of the features that it gives us is why snowflakes tend to form the way they do. This is an up-close picture of a snowflake there.
Is it a real snowflake?
That's a real snowflake under a microscope. Okay? And what we see, guys, is that snowflake has, and I don't know why nobody believes me for some reason, that snowflake has 6 sides. Well, let's say we look at another snowflake and it has 6 sides. And I look at another snowflake and it has 6 sides. Let's say you look at one more snowflake. What do you think it's going to have? 6 sides. And you look at 20 more. What do you think they're going to have? Six sides. Okay. So every single snowflake, guys, is the same in that it has 6 sides. I mean, every snowflake is different, but they all have 6 sides. Okay. That's due to the polarity of the water molecule. Okay. The reason why when a droplet falls, it always tends to form a sphere, right? It forms a sphere. Okay, that's because of the polarity of water. Okay, and if you take your hand, if you have some water and you take your hand and you smack it on the top really hard, it tends to, if you let belly flop, it hurts, right? I mean, it's almost like hitting a hard surface, isn't it? Okay, that's called surface tension. Okay, that's called surface tension, and surface tension is also due to the polarity of water. Huh? No, snowflakes are not circular. All right, so something is polar if they're not equally sharing, okay? But I can also have a nonpolar molecule. And a nonpolar molecule, that doesn't necessarily mean that there's equal sharing. Okay, nonpolar doesn't mean, oh, they're playing nice. It just means that everything's balanced. Okay, so on that water molecule, you saw that the hydrogen were kind of tilted to one side. Okay, that's the reason why it is polar. Okay, if I look at carbon tetrachloride, that molecule at the bottom, okay, what we'll often end up with is carbon in the middle, surrounded by chlorines. Okay, so look at chlorine. Which one is going to hoard the electrons, carbon or chlorine? Chlorine, right? Okay, so this is going to tend to be the negative side, and this will be positive in the middle. Okay, however, since it's negative from every side and positive in the middle, then there's no net charge. Okay, so this is not polar. Because if I'm right here, well, I see a negative and a positive. And if I'm right here, I see a negative and a positive. Okay, so that's considered nonpolar. Yeah? We good? All right. So, a few questions, guys. If I have a covalent bond, it forms a blank molecule. If I have an ionic bond, it forms a compound. Okay? Ionic bonds always occur between a metal and a nonmetal, and covalent always occurs between two nonmetals. It could be three nonmetals, okay, but it always occurs between nonmetals. Which is the stronger bond, ionic or covalent? Ionic, okay. And ionic bonding is stronger because it has what force? The electric force, okay. And that electric force is caused when the atoms become just an I? Ions, okay. So they become a positive and negative, and they're attracted to each other. Let's see, what else? I think that's about everything. We good, guys? All right.